Hey everyone, my name is Brandon Gracely. I'm a high school math teacher. We're going to learn about the remainder theorem. Now, to be able to do this, you have to already know how to do polynomial division. So please go back and watch that video if you haven't already. And we're going to sort of notice how this works just by investigating. I'm not going to prove the theorem or anything like that, but we're just going to notice with a particular example. So let's try this. We're going to divide a particular polynomial. I'm going to call it p of x. That's the function. It's x squared plus 5x plus 6, so just a simple trinomial. We're going to divide that by, I'm going to say each binomial. And I'm going to give you a list of binomials down below here. Now, if you want, just pause the video after I show these to you and go ahead and try dividing them on your own, and then I'll show you the division myself as well. So the list of polynomials is here. The first one is x minus 2. The second one, see if I can squeeze these all in, is x plus 2. Then we're going to try x minus 4 and x plus 3. So there are 4 binomials to try to divide this polynomial by and see what happens. So I'm going to go ahead and do those right now. I'm just going to do it kind of quickly because you're already expert at dividing polynomials. Okay, so for the first one I got x plus 7 with a remainder of 20. Let's try the next one. Okay, for the second one I got x plus 3 with a remainder of 0. Oh, I'm feeling a little cramped here. It's going to be hard to fit everything in. I'll have to write a little bit smaller maybe. Let's see, x positive 42, good number. And last we have okay, we ended up with a remainder of 0 on that one as well. So each of these we divided by a binomial, a different binomial, and we got different remainders, kind of, a couple of them are 0, and then we also have all of these different quotients. So now here's the part where we're going to notice something, and I want you to try this. So evaluate each of the following. So the first one is going to be p at 2, then p at negative 2, p at 4, and last p at negative 3. So there's the polynomial function. Substitute the number 2 in there and evaluate the function to see what the value is. So pause right now if you're going to do that, and in about 5 seconds I'm going to write down what each of those numbers is. Okay, here we go. P at 2 is 20. P at negative 2 is 0. P at 4 is 42. And P at negative 3 is 0. So I want you to just notice that when I divided by x minus 2, the remainder is 20. When I substitute positive 2 into the polynomial, I get that same number, 20. With x plus 2, remainder was 0. Substitute negative 2, and we get 0. Continuing along, x minus 4 gave a remainder of 42. P at positive 4, positive 42. X plus 3, remainder of 0. P at negative 3 also gives 0. And this pattern is true all of the time. And this leads us to the very cool remainder theorem. So let's write this down. When polynomial p of x is divided by a binomial x minus b, the remainder is p at b. So as we had up here, this is just the first part of this. I'm going to add a little bit to it in a minute. So if I had x minus 2, the remainder is the same as if I did p at positive 2. So the sign is always the opposite. Or if you want, the number 2 is what you would put in here to make this 0, is another way you can think about it. Now that's fine if we're looking at a binomial like this, but there's an extension of this where we could have something a little different, like a 2x minus 7, that kind of thing. So I'm just going to write that down right now. I'm not going to show you examples of it to kind of sort of prove it or demonstrate it to you. When polynomial p of x, is divided by, once again, it's a binomial, but the style is a little bit different. It's going to be a times x minus b. So we have a number, a coefficient out there. The remainder is a little bit different. It's p at b divided by a. Now that leads us to a couple of special restrictions. So let's just put a comma there. So the remainder is that. And I also have to say where a and b are integers. And a can't be 0. If a was 0, this wouldn't be a binomial, this would be a constant, and also we would be dividing by a in here, which would be pretty bad. So these are the two forms of it. So when you divide by a binomial, you can determine the remainder by substituting a form of that or a portion of that into the polynomial function and just evaluating that instead of doing polynomial long division. Now we are still going to need polynomial long division. We're going to use this to help us figure out when we need polynomial long division. Okay, so let's try out a couple of examples. Let's find the remainder when p of x equals, let's say 4x cubed plus 2x minus 7 is divided by, let's do x plus 5. Now, one way to do this is to do polynomial division, pad this out with a 0x squared, do the division, which you can see in another video if you're interested in that. So, but our solution here is to use the remainder theorem. So using the remainder theorem, the remainder is, and we can just do p at, now that's a plus 5, so we write negative 5 here. What's p at negative 5? Well, that's 4 times negative 5 cubed plus 2 times negative 5 minus 7. Alright, so a little bit of work here. That's negative 125 times 4 is negative, negative 500. And then we have minus 10 and a minus 7, so that's negative 517. So that's the remainder. And we didn't have to go through all the work of polynomial division to find out what the remainder would be. And once again, that's going to be really helpful to us very soon. Okay, let's do another example. This one where we have a binomial with an a value out front here. So let's find the remainder. When, we'll call it p of x again. We'll give it a different definition. 2x squared plus 3x minus 35 is divided by, maybe we'll do this a couple of times. How about we'll do kind of part A here. Let's do 2x plus 5. Let's try that. So to do that, just write my solution here. I'm going to find p at, now I want to use, it's supposed to be the style, sorry, it's on my other page here. The style is this, ax minus b. Now here I have a 2x plus 5, or that's a is 2, and b is negative 5. So I'm going to do p at negative 5 halves. Now you might be familiar with that from solving quadratics before. If you've sort of noticed in this style, if this is one of your zeros, you would do negative 5 halves to find out what that would be. You could also set this equal to 0, rearrange to solve, and you'll get this value, negative 5 halves. Okay, so let's try this out. 2 times negative 5 halves squared plus 3 times negative 5 halves minus 35. That's 2 times 25 quarters minus 15 halves minus 35. And let's see, that's 25 halves then, minus 15 halves. That's going to work out nicely. Minus 35, I'll just leave that for a second. Looks like 10 halves, which is 5, minus 35 is negative 30. Okay, so that's the remainder. Alright, second part. How about 2x minus 7? So a little bit different this time. We're finding p at positive 7 halves. That's a negative there, so we have ax minus b. A is 2, and b is 7. And it's positive that time. So we have 7 halves, b over a. 2 times 7 halves squared plus 3 times 7 halves minus 35. Okay, that's 2 times 49 quarters plus 21 halves minus 35. Let's see, that's going to be 49 halves plus 21 halves minus 35. Looks like 70. Looks like 70 halves minus 35. Well, 70 halves is 35, so that's actually just 0. Okay, so we ended up with 0 for that one. Nice. So that's cool. So we found something that divides with a remainder of 0 without actually doing the division, just by testing it out. Okay, that's cool. Let's do one more question. This one's a little bit different. Let's find the value of this letter, or this parameter k, so that when this polynomial, p of x, which is 4x cubed minus 5x squared plus kx, we don't know the coefficient there, minus 11. So find the value of k so that when this is divided by x minus 3, the remainder is 16. So if we were just doing long division here, this would be a lot of trial and error to figure this out. But what we know is that because of the remainder theorem, we know that p at positive 3 equals 16. That's what the remainder theorem tells us. I know that I want a remainder of 16, and it has to happen with this divisor, so the positive 3 is where we evaluate this function. So p at 3 is 4 times 3 cubed minus 5 times 3 squared plus, we don't know k, so we'll just write k, and then the 3 goes there, minus 11. Now this has to be equal to 16. That's the equation we've set up. P at 3 on the left equals 16 on the right. Alright, so 3 cubed is 27, and times 4 is 108. And then we have 3 squared is 9, times 5 is 45. I'm going to write 3k now, 3 times k, minus 11 equals 16. So on this side, 3k, and if you collect all this stuff and subtract from both sides, you're going to get, you're going to get negative 36 over here. So just collect like terms and reorganize your equation. Dividing both sides by 3, I will get k is negative 12. So k is the value that, negative 12 is the value for k that will, when you divide the polynomial by this binomial, you'll get exactly the remainder, 16. Okay, thanks very much.